Hello, and welcome to physics lesson 4.02, Newton's first law of motion. So we're going to start a series of a few videos where we go over Newton's three laws of motions. He came up with these in the late 1600s, and these are the same equations that physicists and engineers have been using for hundreds of years. It's the equations we used and the concepts we used to put men on the moon. And if we send someone to Mars, it's these equations, are these laws that are going to help us come up with what we need to do that. So let's go ahead and get started. You should have seen these in your freshman class, but let's go to some videos to help jog your memory. So we've got two videos here. Whoops, need to restart. So video number one. These videos illustrate Newton's first law of motion.
Nixon, yeah, killer.
All right, so that's the first half of the law, and the second half is, oops. All right, so I'm sure you've seen those before, but hopefully that helped jog your memory, and you remembered that Newton's first law is a body in motion stays in motion, and a body at rest stays at rest. That's probably how you learned it. We're going to fill in that definition a little bit. So here we go, Newton's first law. A body in motion stays in motion. And that's what we saw with the fellow riding the bike. The bike hit an immovable object. So the bike had an interaction with the sidewalk, but the man wasn't attached to the bike in any way. And so his tendency is to continue in motion. Nothing was acting on him. So even though the bike was forced to stop, he continued on. The second half is a body at rest stays at rest. So the plates that were on top of the silk tablecloth, he was able to pull the silk tablecloth out quickly, and the plates didn't move because a body at rest tends to stay at rest. But what we need to add to that is unless acted upon by an unbalanced force. So what we really need to spend some time on is defining this unbalanced force. Let's add the rest of the info on this. So the general info. This is also called the law of inertia. And we define inertia as the tendency of an object to remain in motion. Well, what's going to determine an object's tendency to remain in motion? And the answer is mass. So inertia and mass are directly proportional. That symbol means directly proportional mass. When we talk about mass versus weight, we'll get into this a little bit more, but I wanted to just kind of insert this now. So if you have a little kid on a bike and he goes over the handlebars of his big wheel, he has less inertia than the fella in the video did. All right, so let's talk about balanced versus unbalanced forces. And here's why we need to talk about this now. You may have talked about when you learned Newton's first law before, you might have learned it as a body in motion stays in motion and a body at rest stays at rest unless acted upon by a force. Well, there's a difference between being acted upon by a force and being acted upon by an unbalanced force. And it's the details, the devil's in the details in physics. So I'm going to draw the first of what you're going to learn are called free body diagrams. On the first one, we're going to have a block at rest. On ice. And then I'm going to have a block, I'm going to push that block across the ice. Actually, let me change that. I'm just going to give the block a push. So I'm going to stay where I'm at and I'm going to give that block a push. And then I'm going to have the block moving over the ice. And finally, I'm going to have the block when it hits a patch of snow. So it's on smooth ice. By the way, this says ice over here. And it's we push it on ice, it's moving over ice, and then it hits some snow. All right, so let's get our block. Now, I'm going to draw vectors to represent forces. I'm going to say this now, we'll write it out later. It doesn't matter how big an object is, forces that act in a straight line always act as if they're acting on a single point in the middle of the block. So all of my vectors for straight line motion are always going to start in the middle. All right, so take a second and think about these scenarios. There's one force that's always going to be at work in every scenario. Can you guess what that is? All right, hopefully you said gravity. So I'm going to draw a vector representing F sub g, the force of gravity. And it needs to be about the same length in each of these. A little long. I don't think I drew them quite level. So my goal was to make them the same length because the force of gravity, the block doesn't change its mass, and so the force of gravity is going to be the same. Now I didn't draw in the surface. Here's my ice, here's my ice, here's my ice. But anytime we're in contact with the surface, there's that word again, contact. We know we have a contact force known as the normal force. So I'm going to have the normal force. And look what I did here. I attempted to make these two, well, I'll talk about why. I do an F with an sub n. All right, so let's talk about the block at rest on the ice. Those are the only two forces at work. Now, the block is, and motion, I like to do a motion vector. So green, and I always do them in green. Am I at motion here? So if I don't have any motion, I'll usually do an X, but it's not usual that we don't have motion. What I'm doing is motion force analysis. You need to get into the habit of thinking, okay, what are my forces and what's my motion? So here we go. I have a block at rest on ice. I have the normal force acting up, and I have gravity, the force of gravity pulling down. But these forces are equal and opposite. This is called balanced forces. So this is an example of balanced forces. Balanced forces. And I write, there's a term we use, FNet, I'm going to put it up here. I'm running out of space. F net is the sum of all forces. So my F net here is 0. I am at rest. Okay. Let's go to pushing the block. Now I need to add a force. We're going to assume there's no friction because we're on ice. And so I'm going to put, and this is going to be an applied force because it's a push. So I have my applied force, and let's say this is 10 newtons. The other thing that this is going to do is, so I do for motion, I do a green arrow. Then above it, I write what's going on. So I'm going to have, you're going to find out when we do Newton second, that this is going to give me acceleration. So I have acceleration. And let's just say, let's give these some values. Let's say this was a -10 coordinate systems here. Let's say this was a +10. Okay, so let's give those values too. We're going to make all of these worth 10 newtons. What happens? Look, do a force analysis here. So these two forces are equal and opposite. They're going to offset. But here, I have a 10 Newton force in the horizontal. So if I add up all my forces, do I get 0? This is an unbalanced force. I have a force net that is equal to 10 newtons. And look what I've got. I've got acceleration. Okay, next scenario. I have my block moving over the ice. Do I need to add any more force vectors? Oh, by the way, let me back up a bit. I have an error. I tried to make these the same length. I made this vector. I'm going to just fix it right now. If these are all 10 Newton vectors, they should all have just about the same length. So, and that matters. Later on, you'll be graded on the length of your vectors. So hopefully those are the same. Okay, so block moving over the ice. Do I have any more forces to add? If you want to think about it, pause the video here. The answer is no, I don't. Because once the block leaves my hand, I'm not in contact with it anymore. That contact force only applies while there's contact. So I have motion, but if my forces are doing this, what do I know about this motion? I know that I have constant velocity, and I always write that as constant v. This block is moving at constant velocity. So once again, if I added up my forces, my F net is going to be 0. I have balanced forces. So this is a body in motion staying at rest. Now we're acting upon it with an unbalanced force. Here's a body in motion staying in motion. If I could truly have a 0 friction surface, this block will continue moving at this constant velocity for as long as it has space. But here we go. I'm moving along the lake. Let's say we're on a lake, and all of a sudden I hit a patch of rough, snowy, chunky stuff. And now I introduce friction. And I always write friction as F with an FR subscript. This is FN. And let's say this has a force of 10 newtons, and it's going to have to be negative because it's going in the negative direction. Remember, my coordinate system still applies. So now, and before I talk about balanced and unbalanced, whoops. So now, what's the block going to do? We know it's going to slow down, and the word we would use is decelerate. We know my velocity is still going this way, but my acceleration is going to be back that way. So we're going to decelerate, which is basically another form of acceleration. So here I have an F net that is equal to negative 10 newtons. I have unbalanced forces because I have a net force. That's why for Newton's first law, we say not unless we say, we don't just say a body at rest stays at rest unless acted upon by a force. That's why unbalanced is so important. Because we never have a situation where we don't have a force, because gravity affects every object all the time. And if you're not falling, that means there's a normal force pushing up on you. But it is common to have an unbalanced force where we have, if you add up all the forces, now we get a force in a certain direction. When our forces are unbalanced, then we get acceleration. Think about this. We want to say that an object doesn't want to move unless there's force acting on it. That's wrong. So let me just let me grab my red pen. What's one of our big takeaways? It's wrong to say an object's motion is dependent on the presence of a force. What's correct to say is we have to analyze balanced versus unbalanced forces and acceleration. So here, think about it. If I have constant velocity, what do I know? My acceleration here is 0. If I'm at rest, I know my acceleration here is 0. Can you have an object moving and have 0 acceleration? Absolutely. When is acceleration not 0? So let me see if I can squeeze this in down here. Acceleration is present with unbalanced forces. So that's a lot of description for just one little word, but you're going to find it means everything, because when you read a problem, you can't just, if you think that you can come into physics and just start slapping numbers into equations and get answers, you were wrong. Because what you have to do is you have to analyze either the motion and look at the forces that are acting, or the forces and look at the motion. You have to do an emotion analysis almost for every problem from now through next April. So that's why I spend so much time talking about it now. All right, let me make sure I didn't forget anything before I stop the video. Wrote some notes out, and now I can't find them. I got distracted. There was a hawk that just swooped down and got a pigeon right outside my window. So I don't know if that was cool or sad. I guess I'd have to say yes. There it is. Okay. Okay, I think that's all we need to talk about with Newton's first law. Thanks for watching and have a good day.